In the name of Allah, the most compassionate and the most merciful. Hello guys, I'm Salah Qashqai, and in this video we're going to talk about the very interesting concepts in mechanical and structural engineering, which is called contact problem. So based on previous video which we talked about the soil structure interactions, which we run the model with the seismic and also harmonic loading. In this video we're going to add the external spring links as a contact problem. So if during the seismic acceleration displacement reach to this displacement contact, so this structure as a lateral springs as a in x and y directions, it's going to be indicated and connect to the structures to trying to damp the total response spectrum of this structure from this node. So you see guys, these structures have 6 degrees of freedom as a 2 mass in foundation and in the top of the column. And you see we defined 2 springs as a contact problem in horizontal and vertical direction, and also applying the seismic acceleration in x and y. So during the seismic accelerations, if the displacement reach to this position, so these springs going to be connected to the structures. And for definition of the soils, we defined different kind of material properties. You can change it with your own in OpenSees as elastic, no tension, reinforcing steel materials, and also multilinear material properties. My target in these videos is just show you how can we model this kind of soil structural modeling, and I don't use the exact material properties for my modeling. You see guys, if you want to model the exact values for soil and structures material properties, so you can you must have a laboratory test, or even have exact data from site experiment data. So in this example we are going to run 3 types of analysis. First of all, we are going to run the analysis without using this spring as a contact problem, and then seeing the result of the time history dynamic analysis. And then in second analysis we are going to apply just horizontal spring and then seeing the result. And in third analysis we are going to run the horizontal and vertical direction both in the result of our analysis. So 3 kind of analysis to seeing the different interactions between springs and total of the structures. So in first example, you see guys, I defined soil material properties for this analysis. You see in soil we defined 2 springs as a lateral springs and also rotational springs. So this and this is defined as a lateral stiffness properties for soil, and also this defined for rotational spring properties of soil. So I just use the my own data, and it is not the exact values. And if we run the analysis and seeing the different time histories for displacement of each node in horizontal and vertical direction, you see guys, for example in node 1 we have two displacement x and y. I mean this position. In node 1 we have a horizontal and also vertical displacement time history, and also in node 2 in here we have x and y displacement time history. So we are going to apply the seismic acceleration in x and y from 0 to 10, and then after that no applying load is going to be applied to the structure. So, and also we add the initial velocity and also after that running the seismic acceleration. So at the first we applied the initial velocity, and let's see the other outputted data. You see guys, in node 1 and in node 2 different velocity time history results, and also accelerations, and also spring soils reactions, you see guys, and also element based shear outputted data, and also seeing the base reaction and displacement in x and y directions. It's going to be shown in here. So in first example we didn't use the contact in our structures. So in second analysis we use just horizontal contact. So you see in here we use horizontal contact in here, and we define the displacement of the contact. I think I defined 0.2 millimeters for this analysis. All the properties of the soils and structures is the same, and then we run the structures with initial velocity and then applying the seismic accelerations from 0 to 10 second, and then you see in here undamped structures in this time reach to the contact displacement, and then tries to prevent to displacements goes more than this value. So you see guys, in last video we run the uncontact problem, and you see if we run the horizontal contact, so in here the structure's displacements goes to like a smooth line, and like in here, and you see also vertical displacement of the node 2 is going to be damped, and also you see the velocity also is going to be damped, and also accelerations based on this contact which we applied it to the structures. So these structures and also this contact is going to be joined as the same structures. And let's see the other outputted data. You see the horizontal axial force spring, vertical, and you see the moment. You see in this second the moment is going to be smooth because we use the contact spring, and also you see element forces is going to be smooth. So it shows that if we use the contact when the displacements are during the time history analysis reach to this value as a 0.2 millimeters. So this contact problems helps us to prevent the more motion of these structures, and in some cases it helps us, but in some cases it goes to not helping us. So in here you see base reaction and displacement in X and also Y directions based on this example. And let's see the other outputted data as a third example. So in third example we use horizontal and vertical direction as two contact problems, and we run the seismic acceleration. At the first we run the initial velocity and then seismic accelerations, and then all properties is the same as last video and last analysis, sorry. And you see in node 1 as a vertical directions, also you see it's going to be damped, and also in y directions of the node 2. So if we use the contact in node 2 as a vertical and horizontal direction, so this node is going to be prevented to go in vertical, and also this node is going to be prevented to the y directions. And also you see it shows the results. So it shows that if we use the contact problem to prevent the displacement, and it shows us to preventing more displacement and also more velocity and acceleration. You see guys, yes, you see in here we have more accelerations, but after that the acceleration is going to much more less than last analysis. And then you see in here spring forces, reactions, time history, and also moments which we talked about, and then base shear and also displacement and base shear reaction in X and Y directions. So as I showed you, by using contact springs or contact elements, for example in here you can use these structures and then run it again for defining interactions between two structures. So in this example we used two kind of interactions of the two structures, these structures and these structures, and also soil and these structures. You see guys, and you can promote it and change it with your own data. The code is available in my GitHub, and as I told you before, I just want to show you how can we model this kind of complex structures in structural engineering, and I don't use the exact values from laboratory test or even using the experimental data. You see guys, and you can change the model with the exact values for soil and also contact problems interactions. In the other analysis, we are going to run the seismic response spectrum analysis. So we are going to change the total mass of the structures. So the total mass of the structures equals to this value and this value. So we're going to change the total of the structures. So for example, M1 in my model equals to 5% of the total mass, and then mass at the top of the column, which is called M2, equals to 95% of the total mass. And by changing the mass, we're going to run many times to showing you the response spectrum for displacement, acceleration, velocity, and also different springs response spectrum with this defined material properties. Let's see the result. So in response spectrum analysis, all process is the same, but we change the mass and then run it many times to seeing the response spectrum result for displacement with the damped and undamped structures, for velocity, accelerations, you see guys, and different spring forces, and also this values is the last data of the base reaction and displacement in x and y directions. So in first example we use not contact, and in the second analysis we run just horizontal contact, and you see a little changed with this contact actions and interactions between these structures, and also these structures joined together, and you can compare it and seeing the different amplified factors for these undamped and damped structures modeling. You see guys, in this horizontal in x of the node 2, amplified factors equals to 2, and if we applied the horizontal contact springs, so the amplified factors equals to 1. So it shows that the contact helps us to preventing more displacement and help us to damp the total of the structures. And let's see the third example with the horizontal and vertical directions, and run it the response spectrum analysis for different masses. You see, you can see different response spectrum shape, and also different amplified factors, and in here you see base shear and reactions for last outputted data. So let's see the OpenSees file for first contact problem without response spectrum analysis. So in first example, which I told you the result of this dynamic analysis with two masses and with contact problem. So at the first we defined the initial velocity, and then applying the seismic acceleration, and then defining the contact. So this report is awesome guys, which I told you in last video. Please read it and seeing the awesome report. As you see, I defined many functions in here for better plotting the data and also run it. So I defined column properties, and also defining the initial velocity from starting time, which I defined it as a 0, and defined the soil material properties. You can define it with true or false in my OpenSees modeling, and also I defined the seismic acceleration durations equals to 50 seconds. So, but seismic applied just for 10 seconds. And then in here, the column material properties section properties is going to be defined with this number of fibers in x in y and z directions, and also we're going to define the different soil material properties, which I told you in here. Elastic, no tension material properties, reinforced steel material properties, multilinear material properties for definition of the soil properties. You can change it with many kind of force displacement relations, you see guys. So I just use these samples for bettering, showing you can define many kind of the material properties for this modeling with the awesome OpenSees modeling concepts, numerical modeling. It's so awesome for this kind of different kind of material properties in OpenSees. So for elastic soil and elastic no tension soil, we define these material properties for soil, and also elastoplastic soil for horizontal, vertical, and rotational springs. We define these material properties, and also for multilinear material properties as defined as a spring kind 4. We use these material properties, force displacement relations, and also in here moment rotation relations. And you see in here we're going to define the interaction analysis function with definition of the soil node, contact node, and also we're going to fix the some nodes in for definition of the soil, and also we're going to fix the some nodes for definition of the contact, and also definition of the mass. In this example, we just use this mass 1 equals to false in our model, because we want to model two masses in foundation and top of the column. And in this model we use the linear equals to false, because we want to evaluate the column material properties in a nonlinear material properties, and also the definition of this rectangular section as a fiber section, and also definition of the nonlinear beam column elements for better evaluating this dynamic analysis reactions of the materials, and also outputting the displacement, velocity, acceleration, base shear, and also curvature of the elements during the analysis, and also definition of the different kinds of the soils which we told in here. So in here we defined 4 types of the force displacement for spring properties. And also let's see in here we define the soil natural frequency, or I'd better say frequency of this structure, soil structures, with definition of the elastic material properties for soil damping. And in this example we use this so soil damping is true for all the model, because we want to indicate that damping stiffness and soil damping stiffness and for our model. And you see guys, we're going to define the seismic acceleration in x and y direction with initial velocity which started from 0 time, and also we're going to define the periods of the structures in our model. So in this model, the period is true for all the model, and the damping is also true or false during the analysis, because we want to show you different types of the undamped and damped conditions. And also in here, in some cases, the contact is true or false in our modeling, and in example we use just this nonlinear contact force displacement relations, and you can change it for linear one. So for example, you can off it and then turn it on this and then run it to seeing the different response spectrum or even time history result data. And you see in here, we run in here dynamic analysis, and in each step we're going to output the displacement, velocity, acceleration in different directions, and also updating the effective lateral stiffness by, and this value is very help us to evaluating the effective damping ratios of the structures. And let's see in here, if the contact is true, so and displacement of the each step is more than contact displacement, I mean if the displacement of the structures reach to this displacement, so U contact in this picture equals to contact displacement. So if the displacement in node 2 as a horizontal directions as a last data is greater than or equal to the contact displacement, so we're going to add the horizontal and vertical directions. So for example, in here we don't have no contact, so in here we are going to omit these two kind of springs for our modeling. And in second analysis we have just horizontal contact, so we are going to use this. So in second analysis we're going to apply just one lateral contact spring as a horizontal, and in a third analysis we have horizontal and vertical directions springs. So in the OpenSees code we are going to use this both of lateral contact springs for our modeling. And let's see, so you see if we run it just one time, it takes 66 seconds, and we are going to see the different time history analysis for our model with the definition of the contact problem, which I run it for my last outputted data with the vertical and horizontal directions, and you will see the result, and also base reactions of the soil and displacement in horizontal and vertical directions. So let's see the other OpenSees file with the response spectrum analysis outputted data. So in the OpenSees file for contact and response spectrum analysis for using contact definitions, all the material properties is the same as last OpenSees file, and also all functions is the same, but these functions is going to be changed because the better showing of the different response spectrum analysis and also time history outputted data. So I changed these functions for better plotting, and also let's see analyze functions for better converging the data during the dynamic analysis, and also this file is same as last file. All material properties is the same, but in see, yes, in here we defined 50 iterations by changing the mass and then trying to output the data for undamped and damped conditions. So in 50 steps we are going to change the mass, and in each step, let's see the functions. You see, by changing the I, so the mass of the structure is going to be changed, and then in here, in the foundation mass, we use just 5% of the total mass, and in the top of the column, mass equals to 95% of the mass in X and Y directions. And by these 50 steps, we are going to plot the response spectrum outputted data for different velocity accelerations and base shears and other outputted data. So if we are going to plot it after, let's see, after 2542 seconds, the analysis is going to be stopped, and then in here we're going to plot the response spectrum for velocity accelerations and also spring forces for soil reactions, and also base shear, and also in here you can see the time history result for our last data analysis outputted, and let's see the last outputted data base shear and displacement for soils in horizontal and vertical direction is going to be shown in here. And you see I talked about it in beginning of the this video, the outputted data for on contact, horizontal contact, and horizontal and vertical contact response spectrum outputted data result. Let me tell it again, these videos just prepared for educational purpose. I didn't use laboratory tests for soils and also material properties. My target is just show you how can we model the contact problem and also soil structures interactions with the modeling in OpenSees, and that's all. Please have a comment or even email me to tell me about this kind of modeling. Please have a comment. God bless you guys. Bye.